Grigory Dzhavadyan is going to be talking about what he claims to be Vulkan synchronization made easy. Good luck. Take it away.
Hi. Hey everyone, my name is Grigory. I'm a graphics programmer. I've worked at Google, Waymo, a couple other places, but today I'm here in an independent capacity, and I want to talk about synchronization. So synchronization is a complex topic, and when I was researching a way to approach it in a manner that doesn't make me want to tear the rest of my hair out, the answer that I found again and again was render graphs. And render graphs are really good. They can allow you to construct the synchronization within a frame in such a manner so as to extract the maximum amount of parallelism while avoiding conflicts. And they can also allow you to reduce GPU memory usage. These are all things that the legacy APIs, it was basically impossible to do with those, right? But I don't necessarily think that render graphs are the perfect one-size-fits-all solution for absolutely everyone. For a variety of reasons, but I think a good question to be asking yourself is this: so if I didn't have to deal with this pesky problem of synchronization, and I wasn't strapped for GPU memory, would I still choose that approach? Would I still choose render graphs? And in your case, the answer might be yes, I would. In my case, that I want to talk about today, the answer was no. And to explain a little bit better what that particular instance of my case was, let me add some context. So back in 2017, 2018, I started work on a small personal project. I call it Nice Graph. It can be described as a graphics API abstraction or an RHI, if you will, with backends for Metal and, of course, for Vulkan. And so I intended this to be the sort of middle abstraction level graphics API. So think like Metal on easy mode, where you don't have to deal with stuff like placement heaps or manual hazard tracking, or I guess better analog would be WebGPU these days. And as you can imagine, all the complexity of this project went directly into the Vulkan backend because it had to solve a ton of problems posed by Vulkan's inherent low, or I should say explicit nature, not low level. So the initial version of synchronization in this thing was relying on a combination of resource usage hints and some very, very conservative memory barriers, which was not good, and I knew it was not good. So when I eventually started trying to implement support for compute, I decided to attack the problem of synchronization in a more principled way that still preserved like this overall idea that the programmer can just write their code in this easy Metal or WebGPU-esque kind of way, and get nice looking scenes that might be doing some non-trivial stuff. Like for example, in this scene, it's from an engine that is using Nice Graph, the test scene, but there's compute and graphics working in tandem. Compute is handling all the skinning and deforms, like on the character and all this blob there and stuff, and graphics is doing the rendering. But the programmer didn't have to write any memory barriers or anything. It all gets figured out automatically on the Vulkan backend, and it performs reasonably well, maybe not as good as a render graph would allow, but it's reasonable, it's good enough for their purposes, right? And so today I want to talk about what it took me to get there. And if that sounds interesting to you, you should also not miss the next presentation by Albin after the break. So plug for you. So let's get into it, right? Let's consider the very basic case when our application is only allowed to record a single command buffer at a time, right? And I claim that in such case, it is fairly straightforward to automatically synchronize access to resources. And to see why that is, let's consider this simple example, right? We have an image and a buffer. We have a render pass that uses the image as a color attachment, a compute dispatch that writes to the buffer, and finally we have a render pass during which the image gets sampled and the buffer gets read. So I claim that in this case, it is fairly easy to, as long as we keep track of what pipeline stages are touching what resources, it is fairly easy to automatically deduce and emit the correct memory barriers as we go about recording commands into our command buffer. So for example, when we're at the point when we're about to record this final render pass, we have already seen the entire preceding history and we know the context, right? We know that the image has been written to, we know that the compute has written to our buffer, and we know what's about to happen to them. So we can construct both synchronization scopes of the necessary memory barrier, right? And I'm glossing over a ton of details here, but we'll get into those. That's why trivial is in quotes. So things start getting a little bit more complicated when we allow the possibility of having multiple command buffer objects hanging around. And so to understand what that problem is, let's consider another example, which is similar to the previous one. Again, image in a buffer, but this time around, the commands that write to our resources are recorded into command buffer X, commands that read going into command buffer Y. And so now we have this problem that we suddenly no longer have that context that we used to have while we were recording our command buffers. Right? So before we had this entire history of what touched what resource and when. Now we don't have it. So for example, let's say we're recording command buffer Y, we're about to record this render pass, and at that point we don't know whether command buffer X is going to go before or after Y in the submission queue. And actually at that point, the commands that modify resources might not have even been recorded yet. So we cannot make any assumptions. That's a problem. So what's the solution? I call it interim barriers. I've also heard it referred to as patch barriers. It's not exactly a new thing. It's been used in certain places in the industry, but it doesn't have quite the same publicity level as render gaps, so which is one of the reasons I wanted to give this talk. And the solution, it has two sort of ingredients. The first one is to independently track resources on a per command buffer basis. And to explain a bit better what that is, first of all, we introduced this concept of a synchronization state. And you can think of synchronization state as a little piece of data that we use to track accesses to a resource. And we'll get into what exactly it comprises a little bit later. But so anyway, each resource gets a single global synchronization state. And then also for each command buffer that the resource is used in, it gets one local synchronization state. You can see that illustrated on this slide here. And then as we record stuff into our command buffers, we assume that the first access of a pipeline stage to a resource is just not going to require any synchronization. We take that assumption as a given. But we remember those accesses and collectively we'll refer to them as the expected synchronization state. And we store that in our little table there as well. And then we track subsequent accesses of that pipeline stage using the local sync state and using that simple algorithm that I alluded to in the previous slides. So that's the first part, which helps us to get individual, internally well-synchronized command buffers. Now, the next part is comes when the order of submission of our command buffers finally becomes fixed. And so remember, in the first step, we made certain assumptions about synchronization. Once the order of submission becomes known, these assumptions might turn out true, and they might also turn out false. If they turn out false, we need to fix the broken synchronization by patching it up. So how does that happen? In NiceGraph, all command buffers are supposed to be submitted on a single thread. They form a nice ordered timeline of things happening. And so as we go through the command buffers that we are to submit, we look at the upcoming command buffer. We look at all the resources participating in it, take their expected synchronization states, and compare them to their corresponding global synchronization states. As a result of that comparison, it is fairly easy to derive the necessary memory barriers to keep the overall command stream well synchronized. So we record those barriers into a little auxiliary command buffer and submit that before proceeding to submit the upcoming main command buffer, after which the corresponding global synchronization states of all the participating resources get updated. And then we repeat the same procedure for every command buffer in the submission queue. And this is really like the 10,000-foot overview of the method. Like, if you forget everything else that I talk about today, like these two slides are probably the most important thing to keep in mind. But let's get into the gory details, right? I claimed that it's not too difficult to synchronize access to resources within a command buffer. I lied. It's actually not trivial at all. So let's see what NiceGraph does to address it, right? So first of all, we introduced this notion of synchronization request. And you can think of it as a description of intent to touch a resource. It has access mask, stage mask, and layout. You can see the definition of the struct here. But basically what it says is this: such and such accesses in such and such pipeline stages would like to touch this resource. And then for images, also we specify the layout that we want the image to be in. And so synchronization requests are issued at any point in the code when we are about to record some commands that might result in a resource getting either read or modified. So for example, binding a vertex attribute buffer, binding an index buffer, kicking off a transfer operation, or binding a shader resource. And so I should mention that in all of these examples, most of these examples that I listed, it is fairly obvious what the corresponding access and stage masks should be, except for when we are binding a shader resource. In that case, it's not that obvious, but if you do a little SPIRV introspection, which we do in NiceGraph, you can pin down exactly which stages are using a descriptor and how, and so you can keep your barrier masks fairly constrained that way. And but synchronization requests by themselves don't necessarily mean that a memory barrier is going to be emitted. It might or might not get emitted as a result of processing the synchronization request. There's a process that decides, basically based on the resources synchronization state, whether a barrier is needed or not. And that process has to abide by a certain set of rules, which are needed to guarantee both performance and correctness. So here are these rules. Rule number one is that we almost always want to allow concurrent reads, and that is just a prerequisite for being able to extract a certain degree of parallelism out of the whole thing. Rule number two is that only a single access within a single pipeline stage is allowed to be modifying a memory location at a time. This is just needed to ensure correctness. But I should mention that NiceGraph's particular implementation is very suboptimal here because it extends this limitation to the entire range of the resource, right? So if you're writing to, for example, a single MIP level in an image, then everything else is off limits, like all the other MIP levels. And that's not good, but it's a work in progress, whatever. So the third rule is that once an access within a pipeline stage has seen the results of a preceding write, it needs no further synchronization with respect to that resource until the resource is modified again. And this is just a wordy way of saying that we don't want superfluous synchronization. Finally, layout transitions. Layout transitions are read, modify, write. They can change the contents of the resources backing memory, so we need to treat them as writes. And because of that, they make for the single notable exception from rule number one, because two reads that require an image to be in different layouts cannot be made concurrent because there needs to be a layout transition in between. So with that, let's take a look at some more, in even more detail, how synchronization requests are issued and handled. So first of all, as you all probably already have guessed, each command buffer object in NiceGraph has an associated table of all the participating resources. So what do we store in that table? There's a bunch of stuff, but the main two things are the expected synchronization state and the resources local synchronization state, which I already mentioned. And so again, expected synchronization state basically just says, before running this command buffer, please make sure that such and such accesses within such and such pipeline stages do not need to be synchronized with respect to this resource. And if you think back a couple slides, that is exactly what a sync request is. That's why we express the expected synchronization state as a sync request. And then we also have the resources local synchronization state, which is that little piece of data that we use to track access to the resource. So let's take a closer look at it. It has three main parts. The first part is a field that specifies which access in which pipeline stage has last modified the resource, aptly named last writer. The second part is a field that specifies which accesses in which pipeline stages have had the results of the last write made available and visible to them. Basically, are they caught up? Are these accesses caught up with the last write or not? And you should really think of this field as a map from a stage access pair to a Boolean value. And the reason it's expressed as a uint32 is because for the number of different pipeline stages and accesses that we have to deal with NiceGraph and their combinations, less than 32 bits is enough to express this whole table. And it's basically implemented as a groups of 3 bits, and each group corresponds to a pipeline stage, and each bit within the group corresponds to a specific access. And if it's set, then the access is caught up. If it's not set, then the access is not caught up yet with the last write rate. And yeah, finally, we have the layout, which is basically just the current layout for images. For buffers, this doesn't have any particular meaning. So what happens when a pipeline stage needs access to a resource? Let's say you're wrote bind index buffer. So now vertex input stage needs index read access, right? Well, we issue a synchronization request for that specific access and that specific pipeline stage against the resource's current local synchronization state. And remember, local sync states start out as blank slates completely, right? There's no previous writers or readers. And so your first accesses will probably not result in a barrier. And so as long as we did not see a barrier yet, we just update the expected synchronization state with that pipeline stage and that access to keep track of what the command buffer wants the resource to be like when it starts executing, right? So let's take a look at the procedure that actually decides whether a barrier is needed or not based on the sync request and the synchronization state. Broadly, sync requests can be categorized as either modifying or non-modifying, and it should be fairly obvious what these qualifiers mean. I should only mention that if a sync request implies a layout transition, in that case, we treat the sync request as modifying, even if the requested access is a read. And so with that, let's take a look at how non-modifying accesses are handled. So for non-modifying, for read accesses, what we want to first check is whether there had been any preceding writes to the resource. If there had been no writes, then it's fine. We don't need to emit a barrier. We do need, however, to update, to set the relevant bits in the per stage reader's mask, the bits corresponding to the access within the pipeline stage making the request. And that is needed for any future writes to be able to synchronize with these reads. And then if there had been a preceding write, then we first need to check the relevant bits in the per stage reader's mask. If they are set, then we're all good, don't need to do anything. If they're not set, then we need to emit a memory barrier and then update our per stage reader's mask to reflect the fact that we're now caught up with the last write. So that's for reads. For writes, for modifying sync requests, what we have to do first is to catch up with any preceding writes and reads, if there are any, by emitting a memory barrier. And then we need to update the last writer mask because now this pipeline stage and this access are touching the resource. Then we need to zero out our reader masks because it's a new write and no one has caught up with it yet, and then update the current layout. And then there's also some special case handling for image layout transitions, which is kind of boring, and I don't want to get into it too deeply in the interest of time. So when I said emit a memory barrier in the previous slides, I did not mean to literally call command pipeline barrier, of course. What actually happens in NiceGraph is that when a sync request is issued, it's queued up, and then we try to handle a sync requests in bulk at the very last possible moment, right? So for compute, we handle all the pending sync requests before the dispatch. And for graphics, it's a little bit weird because we handle the pending sync request batch at the end of the render pass, but then the barriers get emitted at the beginning of the render pass. And that's because the Vulkan spec limits the synchronization scopes of barriers that are emitted within a render pass instance to just the current subpass. So if you want to synchronize with something outside your render pass, you need to emit your barrier also outside the render pass. But then to even know what you want to synchronize with in the first place, you need to know what commands there are in your render pass. So this is like this whole catch-22 situation, which is unpleasant, but there are a few ways out of it. Which the best one is to just not use render passes at all, just use dynamic rendering. Especially with coming up the local read extension, it's probably the right way forward. But if you're like me, can't rely on dynamic rendering yet, there's a couple ways around it still. You could record your barriers into a secondary command buffer, which you call out to from your main one before beginning the render pass, or you could defer the actual recording of the render pass commands, right? You buffer them up until the user actually ends their render pass instance, and then you go through them, derive the necessary barriers, emit the barriers, and then record your render pass commands, which is actually what NiceGraph does, because I'm a little bit scared of secondary command buffers. They are a bit of an underused feature, and I don't trust that implementations will not have undocumented behavior, let's say. So that's the only reason I did that without the secondary command buffers. And yes, also use synchronization too wherever possible. There is literally no reason to not use synchronization too. There is an emulation layer in SDK that does emulation if like your target doesn't support it. But even if you don't want to ship the layer with your application for whatever reason, it's like not difficult at all to emulate it yourself, as long as you keep your barrier emitting code sort of self-contained to like 1 or 2 functions. So yeah, we definitely use Sync2, because without Sync2, your pipeline stage masks will get very broad and scary, and it looks bad. And also, I believe Sync2 affords the implementation to like merge barriers in a more optimal way. So just use it; it's good. So hazard tracking across command buffers. I already kind of covered this in the beginning of the talk, basically, and I would be repeating myself mostly here, but I do still want to mention one subtlety here, which is related to updating the global synchronization state of the participating resources after you submit a command buffer. So let's say you submitted a command buffer, and now you need to update the global synchronization states of all the resources that participate in it. We can't just collaborate with the last known instance of the local synchronization state, because there might have been some previous writes. So, okay, let me first explain what we actually do and then explain why we're doing it. So what we actually do is we check for each participating resource whether the command buffer has written to it or not. If the command buffer has written to it, then it's safe to just clobber the state because there had been a barrier somewhere. If the command buffer has done only writes, then what we want to do is take the per stage reader's mask from the local synchronization state and merge it into the global synchronization state. And the reason we do it is that there might have been some writes by previous command buffers that future command buffers might want to synchronize with, and we don't want to erase that information from the global synchronization state by clobbering it with the local synchronization state. So I want to talk about limitations of this approach, of which there are many, of course. So first of all, everything that I talked about today is limited to single queue only. Like the NiceGraphs implementation is single queue. And I don't necessarily see a fundamental reason for why this method could not be extended to a multiple queue model, but take my words with a grain of salt because I haven't actually attempted it. And I also haven't thought very deeply about it. So, the second thing is, obviously we don't do any resource aliasing. And at that point, if you want resource aliasing, at that point, just do render graphs. You're probably better off doing that way. Also, NiceGraph doesn't expose memory management in that way anyway, so it's irrelevant for the purposes of this project. Another one, it's a small one. There's no stores or atomics supported for frag and vertex shaders. And this is not fundamental at all. I just didn't need it, so I didn't bother with it. It's easy to add. It will make the implementation only slightly uglier. But, it is a limitation, so I thought I'd mention it. The big one for me right now is poor sync granularity, and there's definitely ways to address it. This is the one that I talked about where we track the entire image and not individual MIP levels. So we could track individual MIP levels, and we could do something for buffers as well, like maybe make the user specify like disjoint regions that they're interested in individually, or maybe we divide the buffer up in pages or something. But all of this approaches also imply we need to do more tracking, like you need to do increasingly more CPU cycles doing just tracking of this stuff. And then you're getting into the business of being an OpenGL driver. So, but the way it's implemented right now works for the user of NiceGraph, and they're happy. It's not showing up on their profiler. It's great. And so another one, and this one might also be fundamental, is that we have to emit memory barriers basically at the very last possible moment, which precludes us from doing like this split barrier thing where you kick off a layout transition and then you overlap it with some other useful work as well. But this is something that render graphs can actually help you with. But with this approach, it's not really possible. Or I don't know, maybe it is. If you know how to do it, come talk to me afterwards. I would be very happy to hear your thoughts. Oh, another one that isn't mentioned on the slide, but I think I should mention is that, so NiceGraph doesn't do bindless. Yes. So this means that our problem is significantly easier, yeah, with bindless, it would be much more challenging. So I want to talk briefly about my dream future. in my dream future, all this code that I spent the last half an hour talking about is just dead and buried because it's been rendered obsolete by a potential, maybe a VK layer Khronos synchronization, hypothetical, that just does all this stuff for me. I really want something like that to happen. I don't know if it will ever happen because it's a lot to ask for, right? It's one thing when you make a bunch of simplifying assumptions that work in your use case. It's another thing to automate synchronization against the entire giant API surface that Vulkan has. But two things. First of all, sync validation seems to cover that giant API surface pretty well. I know, big thanks to the amazing team at Learnergy. Shout out Artem for looking at my bugs. Another thing is that something like that doesn't have to be comprehensive to be immensely useful, right? It makes onboarding or porting so much more easier. And if you are, don't necessarily care about squeezing every little bit of performance out of the GPU, that makes your life easier as well. So I'll leave you with this thought. So VMA, Vulkan Memory Allocator, right? It has solved memory management in Vulkan. Like everybody is using it. Everybody, well, maybe not everybody is happy with it. I don't know if I can make that claim, but it's a widely used library that is a boon to the ecosystem. Like it removes a huge chunk, like a huge barrier, haha, no pun intended, to entry. And it doesn't take away the ability to drop down a level and still do your manual memory management if you really want to. So it's a success story by all accounts. So I would really like to see the same success story repeated for synchronization. Like, why can't we have something like Metal, where you have this, by default, you have like this state tracking enabled, and then when you know what you're doing, you're opting out of it, and you can go, with maximum performance. So yeah, with that, that's all I had. And if you had any questions or you want to tell me how wrong I am, oh my God. Yeah, I see John raising his hand. Yeah, now's the time for that.
Oh, very good talk.
Thank you.
Looking at some of your algorithmic work, I had a strong sense of deja vu. I mean, there's sections of your pseudocode that literally exist at the heart of SyncVal. So I want to first say, effectively what you're doing is what SyncVal is doing, but instead of issuing errors, you issue barriers. And that is a beautiful approach. The other thing I want to say about this approach is whether this applies to your problem, whether this library applies to your problem or not, this is the way to look at that synchronization to get it right. You look at the first access as if it's a blank slate. You keep track of the last access because that's your context. And you look at the things between nothing and first, between first and subsequent, between last and the next first. That is the way. This is the way. So
I feel very validated.
So you cannot do better in your approach to looking at synchronization than to approach it the way this has been approached. So that's the first couple of things. Yes, and you point out that because of the lack of granularity, you get over synchronization. And if you assume that every vertex index you wrote in a compute shader and then you bind it indirectly, there's no way to know what you read, even though your compute shader is only writing the first 100 or the last 100. So that's a challenge to make this more general, but it's still a great approach. And the last thing I'll do is I will throw everybody a breadcrumb for this idea of global state. There isn't a global state. I take that back. There is a global state, but in addition to the global state, there is a per queue state. And this is the way SyncVal does this. That for any queues, so for any queue, it knows the last time it was synchronized with some other queue via semaphore. So I can look back and I can look at the existing synchronization state versus any queue with which I have a dependency. And that's specific to every queue. Anytime I submit to a queue, what the existing synchronization state is specific to that queue and its semaphore relationship to all other queues. So, and that's at the head of each queue. Additionally, there's a global state of all submissions to all for all batches submitted to all queues with which I do not have a synchronization relationship. So once you have those two, you can generalize from a single queue to multi-queue, not lose any state. And like I say, whether this exact library will meet your needs, this is a great way to approach it and a great way to think about it. And if you think about it this way, what you get out of Synchronization will also make more sense to you. So well done. Thank you very much.
Thank you. Thanks a lot.
I'm just going to ask, so you said you don't do bindless.
Yep.
Whether you are planning to do bindless, and do you have anything against the developer telling you what they are touching instead of doing the SPIR-V introspection? Because, I mean, for me, handwriting the synchronization isn't a problem, as in with regards to the resources that I'm touching. The only problem is just patching all of the access masks and the pipeline stage masks, especially with events, because with synchronization 2, you have to make sure that your set event and your wait event, they match exactly.
Right. So just to clarify your question, do you mean that when you say, what do you have against the developer telling you what they're touching? Do you mean like the specific resources or specifying the pipeline stages and such?
So instead of trying to look at the SPIR-V and trying to figure out what descriptor I'm touching, because if I'm using descriptor indexing, I might have a 500,000 image table, and some of it might be like update on use while pending, or partially bound and stuff like that. So you definitely don't want to over assume that. So do you have anything against just me telling you, okay, so this draw call or this dispatch is going to touch this and this?
So no, not at all. Actually, in fact, I kind of skipped this from the talk, but the initial thing that I tried was exactly this, like what I would let the user just specify what exactly they're touching. The problem was that, their renderer was not written with this in mind, and it would like wreak havoc on their existing architecture. It was just the wrong approach for what they were trying to do. And so I just made their life easier by doing this. But in general, yes, you could do something like, it's like a rudimentary, I guess, form of render graph expressed in code. So it's definitely a thing that could be done, maybe in V2, when or if I eventually decide to do bindless. So to answer the first half of your question, whether I'm ever going to do bindless or not, I don't know. So the only project that is currently using this is kind of targeting mobile primarily, and it's not clear whether bindless will become a thing or not. But maybe sometime in the future, yes. No guarantees.
All right, and this is going to be the last question.
Not really a question, just a couple of comments, kind of echoing what John said. So first of all, I think your overall approach is right in terms of the way that you're thinking about state in, state out, etc. Also, the way that you're thinking about updates in terms of sort of tracking the writes as a singular thing and then tracking all of the users. That's basically what we do inside of GL drivers. When it comes to your comments about buffer ranges, welcome to GL hell. This is why we don't like writing GL drivers anymore, because we have to do that, and it is a disaster. Over-synchronization is a huge problem. You can GL buffer some data over here, but while you're reading over there, and did you update it? We have no idea. Typically, drivers will do some amount of range-based checking, but once the buffer gets over a certain size, we just throw up our hands and walk away. So it is, this is like, this presentation is wonderful because like, these are all of the problems that GL has. And part of why we did it in Vulkan and kicked it off in the applications, because theoretically the applications should know better. Or at least maybe by making some of them feel a little bit of the pain, they'll understand what we've been doing for them.
Definitely made me feel that pain.
But in general, like trying to turn this into something that can be used more generally, I think that's a good idea if it can be done. It's a hard problem. I think you're on the right track. I also think that what was just said about bindless, yeah, if you had a mode that is, here's my SPIR-V, please automatically figure out my barriers for me. And then you have another declarative mode where the application says, I know I'm going to use these things, but they're in a bindless table, so you don't know that. I don't think it should be too hard to strap on.
Yep.
And when it comes to like sub-resource stuff, that's all a matter of granularity means overhead, but it also means less barriers, and yeah. yeah, it all looks really good.
Thanks.
And after a light grilling, can we give Grigory one more round of applause?